Okay, so now let's look at some other things that we need to know before we go forward. Okay. All right. So the first thing we should know is about heat capacity. You guys can see the screen, right?
Yes, sir.
Okay. So heat capacity basically is the amount of energy required to change temperature of a substance by 1 Kelvin or 1 degree Celsius. Okay. Basically, the formula that we use is capital C equals to Q over delta theta. This is heat energy. This is the change in temperature. And that's of course heat capacity. Okay. The SI units for this is joules per Kelvin or joules per degree Celsius. Just like that. Now, when we involve the mass in anything, so basically we're making it specific. Look at specific heat capacity. Specific heat capacity is basically the amount of energy per unit mass required to change the temperature by 1 kg, sorry, by 1 degree Celsius or 1 Kelvin. Now, it is denoted with small c and is given by Q over m delta theta. So the main difference is there is a mass. So this is heat, energy, this is mass, and this is the change in temperature. So similarly, then the SI units would be joules per kg per Kelvin or joules per kg per degree Celsius. Is it clear, everybody?
Yes, sir. So is this formula the same as MC delta T?
Q, yeah, same thing. Some people use E over m delta T. I use Q over m delta theta. It's the same thing. Okay. All right. So basically, it depends on how you've studied this in O levels. So it's fine, whatever you use, but you should know why it is being used here. Okay. So this is heat capacity. Now we have latent heat of fusion. So for latent heat of fusion, you need to remember that it is the amount of heat energy required to completely change the state of a substance from solid to liquid or vice versa. Okay, it could also be from liquid to solid. But the important thing is that you should remember that without any change in temperature. So usually this carries 2 marks, first for the first part and the second mark for writing without any change in temperature. So latent heat of fusion is given by LF, capital LF, equals to Q only. Okay, so this is just heat. SI units would be joules. Now, when we go into specific, of course, we need to then add mass into it. So now the definition will change like this. I'll be a clever person. I'll copy this. Copy and paste. Okay. So this would be the amount of energy required. Now you just need to add per unit mass to completely change. When you add per unit mass, basically what happens is that now you will use small l and f over q upon mass. Q gets per energy per unit mass. Now the SI units would be now joules per kg. Is it clear?
Yes, sir.
Okay, this will be fusion. Now, the next thing will be specific, sorry, latent heat of vaporization. So for vaporization, basically the same definition, but the only change in this definition would be the amount of heat energy required to completely change the state. Now you gotta remove, it would be from liquid to gas or vice versa, okay, without any change in temperature. Now for vaporization, it would be capital L V equals to Q, and SI units would be the same. That's just joules. Is it clear, everybody?
Yes, sir. Sir, the value of Q will be given in the question or we have to find it?
Depends. If you need to find it, the other things will be given. They're not very cruel, little bit cruel. So specific,
No, sir, I don't agree with you.
okay, latent heat of vaporization. Now, in this one, it is the same definition, just couple of changes. The moment you see specific, it already means that you need to add mass into it, which means here you need to add the amount of heat energy required per unit mass, and here it should be from liquid to gas or vice versa. So in this one, it will be small l and v equals to q upon m. So they have the same basically formulas. That's joules per kg, like that. Okay, please write this down. Although he's not going to give you like I haven't seen any question related to these with heating or cooling curves, but I really appreciate if you draw these curves, because it will give you a better understanding of the question. Now I'll tell you what I mean by this. So when you're dealing with these, you need to understand that there is something called heating curve. Heating curve means that suppose we have a curve like this. Here you have temperature, suppose in kelvins, and you have energy in joules. Okay. Similarly, we can also draw a cooling curve. A cooling curve would be something like this. So again, temperature in kelvins and Q in joules. Okay, now, so heating curve means that, oh my god. So suppose first line like this, let me make it bigger. Okay, and then a flat line, and then this, another flat line, and then this. Okay, in cooling curve it would be like this. Okay, I need to make it a bit steeper. Okay, now, so basically I would now create some sections that you will see. In this first section, you might see that the temperature is changing because the line is going up, which means whenever the temperature is going to change, you're going to use mc delta theta for finding the um, energy, because when temperature changes, it means that it is being heated, and now to raise the temperature, which means it is specific heat capacity. In this section of the graph, it is a flat line, which means temperature isn't changing. It means that you have to use LF times M, because here melting is taking place. Is it clear, everybody?
No, sir.
So you see, in this particular where I've written melting, it's a flat line. Flat line means that it is staying at a constant temperature, right?
Yes, sir.
So this means that the substance has reached its melting point, and at melting point, it is basically changing the state. So the temperature isn't changing, which means that it is going from solid to a liquid. Do you understand?
Yes, sir.
And we always use latent heat of fusion whenever solid is going. Is being like basically at this point it is changing from solid to liquid. That's, you should know. Okay, and then if you check this out, this section only, then again it is like heating, which means this is mc delta theta. It is changing temperature, so we're using heat capacity. In this section, this is now boiling. How do I know it is boiling? Because it is a flat line. Flat line means that it has reached its boiling point. Is it clear? So the temperature is not changing, it's basically changing its state. And whenever boiling is happening, what do we need to use? We need to use latent heat of vaporization times mass. Is it clear? And finally, when it is raising, I mean the temperature is going up again, so again we have to use mc delta theta. So whenever temperature is changing, we use mc delta theta, and whenever the state is changing, then we have to use either latent heat of fusion or latent heat of vaporization to find heat. Is it clear?
Yes, sir.
Alright, please draw this. I'll be back in just 1 minute. Okay. Now let's look at the cooling curve. Okay. In the cooling curve, basically, in the first section you might see right here, the temperature is changing, which means you got to use mc delta theta, right? In this section, you might see that the state is changing because the line is straight. It means you got to use LV times m because it must be going from gas to liquid. Okay. Sorry. All right, now in this section, oh my god, this is where you again this temperature is changing, so mc delta theta. In this section, use LF times m because state is changing, and this section it is mc delta theta again. So here you have condensation happening because gas is going to liquid, and here it is freezing happening. Any questions?
No, sir.
So now you can actually, whenever a question comes, you can actually see what we basically require. Okay. Now, before I go to the basically their experiments, I just want to do some questions with you so that you understand what I mean by these curves. Okay. So, example 1. In example 1, it says that given specific heat capacity of iridium is 1298 joules per kg per Kelvin. Okay. And its specific latent heat of fusion is 26 kilojoules per mole. Okay. Now it says determine amount of heat required to change temperature of solid iridium from minus 15 degrees Celsius to 3015 degrees Celsius. Okay. If 5 kg iridium is heated. Okay, so this is given. Now they've also given the melting point of iridium, which is 2466 centigrade, and atomic mass of iridium is 192. Okay, is it clear? So this is the question. Now, if I were you, right, I would not directly start this question. I would actually, on the side, I would rather create a heating curve. The reason behind this is because I want to know what processes are involved in this. First of all, I should remember that the starting point is actually minus 15 degrees Celsius. So we are looking at temperature in degrees Celsius, and then we have energy in joules. So when you want to go from minus 15 to 315, we also know that it will start melting at this temperature. It means first we need to raise it to this temperature, which is 2466, and then it will start melting. And after it has melted completely, it will then again go up to 3015 because we need to raise the temperature. Is it clear? By doing just this, I can now understand that from minus 15 to this, I need to use mc delta theta. And at this section, I have to use LF times m. And for this section, I have to use mc delta theta again because the temperature is raised. If I don't do this, then I will probably miss out that it also melts in between. Is it clear?
Yes, sir.
So now the total energy, the total heat required would be mc delta theta, which is basically the first part, then latent heat of fusion times mass, that's the melting part, and then we have to raise the temperature again to the final temperature like this. Everybody understands this? So this should be my final equation. Okay. Now
Got it, sir.
the issue is that in this question there is also one more trick being played here, which is basically the latent heat of fusion is given in 26 kilojoules per mole. So we got to change this. And how do we change this? We need to understand that it says it has 26,000 joules in 1 mole. And we know that in 1 mole, basically 1 mole of iridium would be 192 grams, because that's the MR, right?
Yes, sir.
So how, if I want to change it into kgs, right? So what do I need to do? In 1 kg there are like 1000 grams. So how much energy will be there? So I need to cross multiply this. So when I cross multiply, it will be 192 times x equals to 1000 times 26,000. Okay, this is going to get me 1.4 times 10 raised to power 5 joules per kilogram. Is it clear, everybody? So now I have learned how to change latent heat of fusion from moles to kilogram. Any questions?
So could you just repeat the last part, the one that you just explained, with
Yes.
the moles and all?
Yeah, okay. So let me do it nicely then. So what I'm claiming is that 26,000 joules is equivalent to 192 grams. Okay. So why am I saying this? Because I learned that moles are equivalent to mass in grams over mr. Remember? So
Yes, sir.
for for 1 mole, like for 1 mole, I need to find the mass, and the mr is 192. So the mass would be 192 grams of in iridium. 1 mole of iridium is equal to 192 grams, right? So if basically 26,000 is per mole, which means that it is equivalent to 192 grams. Is it clear? Like that.
Yes.
Then 1000 I took because I need to take in 1 kg. So 1 kg would be 1000 grams. So I cross multiply this, and then I'm gonna get it in kgs. Is it clear?
Yes, sir.
Okay, now check this out. Now everything becomes so easy because I got the mass, which is 5 kg. So I'm gonna put 5 here. The heat capacity is 1298, and now I need to check the temperature. So it goes from 24 minus 15 to 24. So I'm going to write 2466 minus 15, because you don't have to ignore the sign. Then latent heat of fusion is 1.4 times 10 raised to 5 times 5 kg plus 5 times 1298 heat capacity times, now it goes to 3015 from 2466. Check the equation. If you do not understand something, please let me know. So when the meeting ends, please rejoin, okay? Now this is going to give you 2.0 times 10 raised to power 7 joules of heat energy. Any questions?
No, sir.
Okay. Now let's do another question. So this was actually pretty simple. Only the mole thing was difficult, so I just wanted to point that out. If this comes, you need to be aware of it. And then let's do example 2. In about 7 minutes, the class will end, so you have to rejoin. So 200 grams of coffee at initial temperature of 80 degrees Celsius and 2 ice cubes of 20 grams each are dropped into coffee. Okay. Without any heat escaping. Now they say the thermal equilibrium is reached. Okay. So they say determine this thermal equilibrium temperature. And now they have also given some of the data. Okay. So for coffee, they have written that C equals to 4.18 joules per gram per degree Celsius. Initial temperature is given as 80 degrees and the mass is 200 grams. For ice, they have given latent heat of fusion as 334 joules per gram. Initial temperature minus 15 degrees Celsius. Heat capacity is 4200 joules per kg per Kelvin, and latent heat of vaporization is 2230 joules per gram. Is it clear, everybody? So this is everything given.
Yes.
Now this basically is the same question as we did, one of the examples where one of the questions which Gatika asked, right? So heat will be gained by ice, and when ice will turn into water, and the heat is lost by coffee, the same amount, right? So the principal equation we need to understand is that heat gained by ice and when ice melts to water should be given by heat lost by coffee. So this should be the first thing I should remember. The other thing I would actually tell you is, if you look at the data set, every data is in grams except for this one. So I gotta change it into grams because it is like, if I change kg into grams, basically I have to divide because it is kg inverse, so I have to divide by 1000. So if I change this, this will be 4.2 joules per gram per Kelvin. Do you guys understand how I did this?
So can you explain again?
See, you have 4200 joules per kg per Kelvin, right? If I want to change kg into grams, what do I need to do? I need to put 1000 grams times kelvins, right? So 1000 divides,
Yes.
it will be 4.2 joules per gram per Kelvin, like that.
Okay, sir.
Okay. Acha. Now let's go forward. Now to understand what's happening here, I would like to draw a cooling curve and a heating curve. Okay, so I'm gonna do it on one diagram, but you can actually use multiple diagrams for it. It's all right. First of all, I should remember. Okay, so I'm putting temperature in degrees Celsius here and energy in joules here. So for ice, you should remember that it is at minus 15 and it goes to 0 first. At 0, ice will start to melt, and when it has completely melted, it will become water, which will raise its temperatures to some equilibrium temperature that we call theta F, final temperature, right? Whereas for coffee, I'm going to use another color. So for coffee, it was at 80 degrees, and coffee basically does not melt or do anything else. It just goes to, it reduces temperature to that equilibrium. So this is for coffee, and this is for ice. Is it clear? Sorry, let me write
Yes.
ice here and water here. Okay. So now I can see for ice, I need to use mc delta theta here. I need to use LF times m here. And for water, I need to use mc delta theta here. Any questions? Okay. Now, so first of all, what is happening on the ice side? Let me write it down. So basically, ice will raise its temperature to 0. Then it will start melting. Then it will become water and raise its temperature, and all of this is coming from basically the energy that is basically given by coffee, and it's because it's changing in temperature, I'm writing mc delta theta. Everybody understands this?
Yes, sir.
Now let's put in the values. So there were two ice cubes. Two ice cubes means if each was 20 grams, it means that total is 40, right? So I'm going to write 40 here. In fact, I'll start from here because this will be big equation. This will be C is 4.2, and delta theta, basically it goes from 0 to, I mean, minus 15, like this. So I got the first change. Now latent heat of fusion of ice is 334 times 40 grams plus, when the ice melts, so 40 grams water will form, which means 40 grams. 4.2 is the heat capacity, and the delta theta basically goes from the final temperature from 0. Is it clear? On one side,
Sir, where is 40 grams coming from?
it's one ice cube is 20 grams, so there are two ice cubes. Okay, wait a second, please. All right. So you guys can see and you can hear me.
Yes, sir.
Yes, sir.
So 40 Suman is the mass of the ice cubes. So 1 is 20, so 2 ice cube means 40, right?
Oh, okay, sir. Got it.
Now, so coffee's mass was 200. The heat capacity of coffee is 4.18. And now it goes from basically, now this is the tricky part. So basically you need to put the higher temperature minus the lower temperature. That would give you a positive answer for the change in temperature. Okay. Any questions now? Now, if you solve all of this, the final temperature that the both reach will be 50.8 degrees Celsius. So, my basically, what I'm telling you right now is that without the heating and cooling curve, although it is not necessary, they will never ask you for this. But without heating and cooling curve, it is very difficult to visualize that what exactly you're achieving. And if you don't visualize what's happening, then you would probably mess up with one of the equations. All right? Okay. All right. Abdul Moiz, everybody understand this? Katika, Suman.
Yes.
Yes, sir.
I hope you're not finding this too difficult, right?
No, but I guess with more practice it'll be easier.
Yes. You need a lot of practice in this, though. That's fine. You guys are gonna do well. Don't worry about it. Okay. Now let's give me one more second.
The thing is, there's just like lots of values and numbers. That's the only thing why it's a little confusing.
Basically, if you learn how to make the equation, the main equation, then basically the question is solved. If you fail in making the main equation, of course it will be wrong. And mostly these questions are like 4 marks, so we can't afford to lose these. So you should basically practice. This chapter is pretty big and has so many questions, and it's like in every paper this question comes. So I mean this chapter comes. So you need to practice a lot. You'll find a lot of questions on this too. All right. Now let's.
So can you show how you solve this equation? Because for some reason I'm messing it up.
Okay, I can do that. No problem. Wait a second. So first I'm going to do 40 times 4.2 and this will be 15. So I got this plus 334 times 40. So I got 15880 plus 40 times 4.2. That's 168. 168 theta final. And then I'm gonna write 200 times 4.18 times 80. So that's gonna be 66880 minus just this 836 theta f. Now just rearrange it. So what you're going to do is 168 plus 836 would be 1004 theta f, and 66880 minus 15880 is 51000. So theta f then will be equal to divided by 1004, so it is 50.8. See?
Okay, sir. I guess I messed up the multiplication part.
If you can't do it like in a go, take some steps. It's fine. Better to be safe than sorry, you know. All right. Now let's look at some of the questions from this, and then we are going to go towards, I mean, the next class. This chapter is a bit too long. In the next class, we're going to look at the other things. So see, wait a second. So I don't know where the thermodynamics was. Let me check. This was thermal properties 117. Right. 1117. Okay. It should be somewhere after this. Okay.
Sid,
Yes.
how much time left in class?
Rafe, uh, it's still 7. Why?
I have to pick up my little cousin.
Can you watch the recording for the questions then?
Yeah, Joyaj.
Okay. I will see you then, okay?
Yeah, Hafiz.
Allah Hafiz. Okay, so this question seems like pretty simple to me, but I don't know. So let's see. So first of all, in this question, you might see that it's like talking about um, that the heater of electric kettle is 2.40 kilowatts. When the water in kettle is boiling at steady rate, the mass of water evaporated in 2 minutes is this. The specific heat vaporization is also given. Calculate the rate, calculate rate of loss. Whenever this word comes, right? Rate of loss of thermal. Rate basically means that it is talking about thermal energy over time, which means he wants us to calculate the power. Okay. So it says during the boiling process. So I don't think this is too hard. First of all, what you're gonna do is we have the mass, right? We already know this is boiling, so Q will be equal to LV times M. Do you guys agree? So latent heat of vaporization is 2260, and the mass is, this is also in grams, the mass is also in grams, so I'm gonna just multiply this. So this is gonna be 2260 times 106, that comes out to be 239560 joules of energy is basically um, taken in to do this. Now we have time as 2 minutes, which means that power will be energy over time. So this will be 239560 divided by, I gotta change this because it's in watts. I want time to be in seconds because it's SI units. So 2 times 60, which means I'm changing 2 minutes to seconds. And now I'm gonna divide this with 2 and divide by 60. So it is going to be 1996.3 watts. Is it clear, everybody? Now, the interesting thing is it says calculate the rate of loss of thermal energy. This is the output we are getting. Do you guys agree? However, the input was equivalent to 2400 kilowatts, watts. How do I know this? Because it says electric kettle has a power, so this is the input. So now we should understand, it's from O levels, that input is equal to output plus the wastage. So input is 2400, that is almost like 2000 plus wasted or the loss. So that is going to be 2000, 2400 minus 2000, that is going to be 400 then. Is it clear?
Yes, sir.
So this was just a trick of the loss thing. Let's look at another question then. I want to find a very, well, this is not the one I want to look at. the effective microwave power is this, the temperature rises to this in 2 minutes, calculate the value of specific heat capacity. This is very simple, you can actually do it with one equation, I think. Um, I don't know, can you do it or should I do it? There's just one equation, Q is equal to mc delta theta, because the temperature is changing, right? I want to basically do one difficult one that I can't find so easy here. Wait.
Sir, how is all this so easy for you?
Because I've solved them so many times. That's why. Well, I haven't solved all of them, but I think mostly students ask and I solve it, so I'm in practice. Determine the specific heat capacity. Okay, you can't do it. This one. Oh, yeah. This is exactly the question I'm looking for. Okay, I want to. That's why I've done this with other people as well. Okay. Now, what we are going to do is I'm gonna basically ask you. My god. This won't even erase the evidence. Wait, it's going. Google. Fine. Okay, this is the type of question that we're looking for. And let's just. Okay, I have drawn all the cooling curves. My god. Wait. Okay, all evidence is gone. So let's do it now. So, first of all, it states that aluminum can of mass, so there's aluminum can of mass 160 grams, contains 330 grams of warm water at a temperature of 38 degrees Celsius. At a mass of 48 grams of ice at minus 18 is taken from freezer and put into water, the ice melts and final temperature is this. So this is the equilibrium they reach. Okay. Now they have given you heat capacities as well. It says, assuming no change of thermal energy with the surrounding, show that the loss in thermal energy of the can and warm water is this. So first of all, we need to look at, we need to draw the curves, right? So what's really happening here? This is for can and water. I think they were at certain temperature of 38 degrees. So they start from 38 degrees and they would reduce to a temperature of equilibrium which is 23. Right? So this is for can and water. For the other one, for ice, you should remember, ice was at minus 18. It goes to 0 first and then goes like this and then raises temperature to, it is exactly the same type of question that we did for coffee and ice, right? Now, we know that this is like mc delta theta, this is LF times m, this is mc delta theta. Now, it says show that the loss of thermal energy in can of water. So it's only talking about the can right now. So we can only look at this one then. So Q equals to mc delta theta. The mass of basically we have to make two equations. We need to make it for water because it has a different specific heat capacity, and can. So we're gonna write mc delta theta for that too. So the mass of water was somewhere given. It was 330 and mass of can was 160. Okay, so water was 330. The heat capacity of water is 4.18 and the temperature change was 38, always the bigger number minus the smaller number, plus the can was 160. The heat capacity of can was aluminum 0.910 multiplied by, it also comes to the same temperature, right? So let's see if we can show this. 330 times 4.18 times 38 minus 23. So this is 20691 plus 160 times 0.910 times 38 minus 23. Make sure you basically put the brackets. So if you add them together, plus 20691, so they come out to be 22875, which is approximately equal to 2.3 times 10 raised to 4 joules shown. Is it clear, everyone?
Yes, sir.
Okay, so this was simple. Now in the next part it says use the information in I to calculate the value of latent heat of fusion of ice. Now what is exactly happening? So the same thing, heat gained by ice plus water would be equal to basically can plus water, heat loss, right? So we already have this, we have found this in the previous part, but this one would be mc delta theta plus latent heat of fusion times mass times plus mc delta theta. Now the mass of ice was 48 grams, so we're going to use that. 48 times heat capacity of ice was 2.10, and the temperature change was 0 minus 18. So first it will reach to its melting point, plus latent heat of fusion, what we need to find, it is also 48. This is in grams, so we don't need to change anything. Plus mass was 48 when it changed to water, so 4.18. So most of the students make this mistake where they don't consider water to be formed, and it goes from 23 minus 0 equals to 2.3 times 10 raised to power 4. So let's do this, and this is gonna be 48 times 2.10 times 18 plus 48 times 4.18 times 23. So this is 6429.12 plus 48 times LF equals to 2.3 times 10 raised to power 4. Okay, so basically 2.3 times 10 raised to power 4 minus 6429.12 divided by 48. So that would be 345. Is it clear, everybody? So simple, right? Now